Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fuad bin Omar from Polytechnic Tuanku Syed Sirajuddin. Now I would like to present about comparative study of microinverters topologies and control scheme for photovoltaic application. Introduction. Figure 1 shows the microinverter design that is combination of photovoltaic system, converter, inverter, filter and load. The MPPT used to control the switching of the converter. Then the microinverter design of the study was the comparison of multi-stage isolate microinverter. The objective of the study, first to design 6 types of microinverters, namely flyback converters, interleaf-flyback converter, push-pull converter, half-bridge converter, full-bridge converter, and current-fed converter by using MATLAB. Second, to simulate the output waveform of voltage VAC, the current IAC, voltage DC link VDC, and the percentage of spectrum THD. Number 3, to evaluate by comparing the 6 types of microinverter design in terms of the spectrum THD percentage, number of components used, and transformer ratio, and propose the best model. Table 1 shows the specification of photovoltaic, maximum power 175.0914 watt, open circuit voltage 43.99 volt, short circuit current 5.17 ampere, and voltage at maximum power point 4.78 volt. Table 2 shows the requirement of microinverter, filter 5 mH for inductor and 1 microfarad for capacitor, V in 110 volt, VDC 405 volt, Vout 230 volt RMS, Iout 0.923 ampere, and converting switching frequency 100 kHz. DC to DC converter. The DC-DC converter circuits were used in microinverter to increase the voltage source 110 volt up to 400 volt. All the DC-DC converter designed in microinverter were isolate types. A capacitor is mounted on the output DC-DC converter, or known as DC link, for the purpose of stabilizing the output voltage. The MOSFET is used in DC-DC converter as a switch due to its faster switching speed. In this study, 6 types of DC-DC converter circuit have been designed, namely flyback converter, interleaf flyback converter, push-pull converter, half-bridge converter, full-bridge converter, and current-fed converter. DC-DC converter design. Figure 2a shows the flyback converter design. The basic operation of the flyback converter is similar to that of the buck-boost converter, which energy is stored in inductor LM when the switch is closed and is then transferred to the load when the switch is open. Figure 2b shows the interleaf flyback converter design. The design of the circuit consists of 2 flyback converters connected in parallel. Figure 2c shows push-pull converter circuit that consists of 2 MOSFET as a switch M1 and M2, a center tap transformer, and 4 diodes. Both switch M1 and M2 are ground reference that makes simpler gate drive circuit and easy control of the power device. While the switch M1 and M2 are alternately turned on and off, the power has been transferred to each primary of the center tap transformer. Figure 2d shows a circuit of current-fed converter that is a modification of the push-pull converter. The inductor LM has been shifted from the transformer output side to the input side. Figure 2e shows the circuit of half-bridge DC-DC converter. A half-bridge converter is a type of DC-DC converter similar operation with push-pull and current-fed converter. Figure 2f shows the circuit schematics of a full-bridge converter that consists of full-bridge power converter S1 to S4, a higher frequency transformer, a bridge diode, and an output filter. The diagonally opposite switch S1 and S4, or S2 and S3, are turned on and off alternately in a portion of each half cycle of switching frequency. Next, H-bridge inverter. Figure 3 shows the circuit H-bridge inverter. The inverter operates by using MOSFET as switch and the voltage output produced depending on which switch are closed. The switch connection for this inverter is a combination of S1 and S4 to produce positive VDC, while S2 and S3 to produce minus VDC. This switch combination will be on and off alternately. Notice that at the same time, S1 and S2 should not be closed, nor should S3 and S4 be closed as shown in figure 4. To control the switching of inverter, pulse width modulation (PWM) unipolar switching scheme was designed. Here is figure 3 for H-bridge inverter and figure 4 PWM signal of inverter switching control. Maximum power point tracking MPPT. MPPT is used to extract full power from the PV array. The perturbation on observation (PNO) is one of the MPPT techniques used in the design proposed. PNO have two types. First, PNO by using the method of MPPT with reference voltage control. For this type, applied to interleaf flyback, push-pull, current-fed, half-bridge, and full-bridge converter. Second, another one is PNO by using the method of MPPT with direct duty ratio control. For this type, is applied for flyback converter design. For flyback converter circuit. Figure 5, A and B show block diagram and algorithm block to implement of PNO by using the method of MPPT with reference voltage control, while figure 6, A and B show block diagram and algorithm block to implement of PNO by using the method of MPPT with direct duty ratio control. Figure 7 shows the full circuit of the flyback microinverter design using MPPT PNO based on direct duty ratio technique. Figure 8 shows the full circuit current-fed microinverter design using MPPT PNO reference voltage control technique. The output waveform of microinverter. Observation to microinverter simulation focus on waveform which is voltage VAC, the current IAC, and voltage DC link VDC. Figure 9A is the output waveform for flyback. Only in the first cycle it is found that voltage and current waveform need 0.02 second times to stabilize. Figure 9B is an output waveform for interleaf flyback. The value of VAC, IAC, and VDC are matched with the requirement. In the first cycle, show that voltage and current output just need 0.01 second to stabilize. Figure 9C is an output waveform for push-pull. Observe the first cycle, the value is less than half value and takes 0.05 second to stabilize. Figure 9D is an output waveform for push-pull. Observe the first cycle, the value is less than half value and takes 0.05 seconds to stabilize. Figure 9D is an output waveform for current-fed. The first cycle, the value is less than half, same with the output waveform of push-pull and takes 0.05 seconds times to stabilize. Figure 9E is an output waveform for half-bridge. The first cycle, the value is less than half and takes 0.03 second time to stabilize. And Figure 9F is an output waveform for full bridge. The first cycle, the value is less than half and takes 0.03 second times to stabilize. Next, the result of spectrum THD of microinverters. Figure 10A shows the spectrum THD of flyback with 1.24% THD. Figure 10B shows the spectrum THD of interleaf flyback with 2.71% THD. Figure 10C shows the spectrum THD of push-pull is 1.47% THD. Figure 10D shows the spectrum THD of current-fed is 1.26% THD. Figure 10E shows the spectrum THD of half-bridge is 2.39% THD, and Figure 10F shows the spectrum THD of full bridge is 2.38% THD. Next, the table shows the comparison of SiC design of microinverter. The percentage of THD obtained from this simulation is low, which is less than 3%. This shows the lowest percentage of THD is flyback microinverter, and the highest percentage of THD is interleaf flyback microinverter. All of microinverter have the output waveform has time delay between 0.01 second to 0.05 second to reach a stable value. By comparison of SiC microinverter design, the flyback microinverter was proposed. due to the value of THD 1.24%, less number of components, and the transformer ratio value of 3.7. Conclusion. The microinverter design of this study was the comparison of multi-stage isolate microinverter, that is the combination of photovoltaic system, converter, inverter, filter, and load. The design type of microinverters produced is flyback, entirely flyback, push-pull current fed, half-bridge, and full-bridge. The MPPT used in the design of all microinverters is to control the switching of the converter. This study used the method of perturbation and observation (PNO) through two techniques, namely MPPT with reference voltage control and MPPT with direct duty ratio control. All designs have met the requirement of Vout equal to 230 volt RMS, Iout 0.923 ampere, Pout equal to 300 volt, and output frequency equal to 50 Hz. Based on this study, all designs produced need to achieve a VDC value of 405 volt to obtain an output value at a load of 325 volt peak or 230 volt RMS. All designs are using MOSFET as a switch with a frequency value of 100 kHz for converter switching and 20 kHz for inverter switching. All microinverter designs produced also have a THD value of less than 5%. This study proposed the flyback microinverter design due to the value of THD, transformer ratio, and the number of components. And thank you.